Hi, Brynn. I hope you're doing well. I thought it would be just as easy for me to do this in video form. Take me just as long if I wanted to write it out so that you could understand what I was writing. So I think this is more efficient. I want to just go through the question here. There's three pieces of information you're given. One is a function f of x, one is a function g of y, and the other is, well, it's not a function that you're given, but you're asked to find g double prime of pi over 6. And the reason why you need that middle equation, this equation here, is because what we're going to do is take g of y, which we know, and we're going to have to differentiate that with respect to y to get g prime of y, and then we're going to have to differentiate that one more time with respect to y to get g double prime of y, because we're after g double prime of pi over 6. So once we get g double prime of y, we can put pi over 6 in. So what I'm going to do is start off with g of y, which is the original function that has not been differentiated yet. It's equal to the integral from 2 to y of f of x dx. And this is why this question is so confusing. You've got all of these different variables being mixed up into these weird combinations. But let's go ahead and let's differentiate this. So what I need to do is differentiate both sides of this. Actually, before I do, I'm going to write g of y. So this, I haven't differentiated anything yet. I'm going to tell myself that when I have the integral of a function, I'm going to introduce that antiderivative notation that you learned about last year. And I don't know if you use this notation in university, but here's an example of where it becomes useful. The antiderivative of f of x is capital F of x, and the integral from 2 to y will be this. I hope you remember that from last year. And that means that g of y will be equal to the antiderivative of the function f of x at y minus the antiderivative of the function f of x at 2. Now keep something in mind for the next step, and that's that the antiderivative of the function at 2 is going to be a constant. It doesn't matter what f of x is, the antiderivative of the function when you put a constant in it is going to be a constant. So now I'm ready to determine the derivative g prime of y. But I'm going to add something here that's, it's really not necessary in this step, but it will be in the next step. Rather than me just throwing a prime on top of this, rather than me just doing that, which is it's not a very informative piece of information, what I'm going to do is say that I'm going to differentiate that with respect to y. And I'm going to differentiate this with respect to y. I really want to highlight that there's an independent variable here that we are differentiating both sides with respect to. So I'm taking the first derivative of g of y to get g prime of y. I'm taking the same first derivative of the right-hand side. And you can go back in the video and see where that right-hand side came from. Briefly again, the integral of f of x is the antiderivative of f of x. And it's going to be evaluated from the lower boundary, which is 2, to the upper boundary, which is y. And then all of a sudden, the x changed to a y because I'm substituting in the antiderivative at the upper boundary minus the antiderivative at the lower boundary. That's why this becomes a y and this becomes a 2. Now, you learned in high school calculus, and also I'm sure it's come up in your calculus course, that when you differentiate a sum or a difference, you can differentiate them separately. So the right-hand side here becomes the derivative with respect to y of the antiderivative of the function at y minus the derivative with respect to y of the antiderivative of the function at 2. And over here, we've got, I'm going to use g prime of y now, okay? But remember, it's with respect to y. So what I end up with is g prime of y equals f of y, because the derivative of an antiderivative takes you to the original thing. So if capital F of y is the antiderivative of y, and I differentiate the antiderivative with respect to y, I'm going to be left with y. The derivative of the antiderivative of the function at 2 is 0 because the antiderivative of the function at 2 is a constant, and the derivative of a constant is 0. So this is where the first part of that solution comes from. There's one of the very first things it says, and it doesn't explain it, it says, well, since all of this is true, that means the first derivative of g with respect to y is f of y. Okay, so now what we need to do is we need to differentiate the first derivative. And here's where things get very, very slippery. You were told, I'm just going to scroll back up and look at it, you were told that f of x is this thing. Right here, this is f of x. So I'm going to write this on another page. F of x is equal to the integral from 0 to sine of x of 4 plus t squared dt. And we know that g prime of y, we just figured out that g prime of y is f of y. That's what we concluded on the previous page. This statement here that I'll highlight for you, this statement is the conclusion that we arrived at when we started here and we went through. And by the way, you had mentioned the fundamental theorem of calculus. What I have in the green brackets here is the fundamental theorem of calculus. That an integral from a to b is the antiderivative of the function at b minus the antiderivative at a. But you can see on the bottom of this screen that you're looking at right now, that is the statement I have here. So what I'm going to want to do is differentiate this f of y with respect to y, because what this is telling us, what it leads us to is that g double prime of y would be equal to f single prime of y. In order to go from g prime of y, which is right here, to g double prime of y, then I have to differentiate with respect to y, so I'm going to end up with f prime of y. And we're after g double prime of y. Okay, so what is f of y? Well, f of y is what we get when we put y in every place there's an x in f of x. You know, you're taught this in early high school. You know, if f of x is 3x, then f of 5 is 3 times 5. F of r is 3 times r. So f of y is found by replacing all of the x's in f of x with y's. And believe me, I don't really, Brynn, when I said in an email, this is a very complicated question, this is not a simple question. So that means f of y is the integral from 0 to sine of y times the square root of 4 plus t squared dt. And now I'm going to introduce another function. I'm going to let f of t equal the square root of 4 plus t squared. This will allow me to use the fundamental theorem of calculus. So what this is going to look like now is g prime of y is going to be equal to the integral from 0 to sine of y times f of t dt. So what does the fundamental theorem of calculus say? And I'll just slow down for a second here just to make sure you're catching my drift. if f of t is the square root of 4 plus t squared, then that's all I've done. I've changed the square root of 4 plus t squared to f of t. So what does the fundamental theorem of calculus have to say about what this is equal to? Well, what that is equal to, which is g prime of y, is the antiderivative of f of t evaluated from 0 to sine of y. That's what the fundamental theorem of calculus says. That's all it says. The fundamental theorem of calculus says that the antiderivative or integral from a to b of a function, I'll use f of t because that's what we're dealing with here, dt, is equal to capital F of b minus capital F of a. And it seems like such a simple thing, but it's so useful in trying to wrap our heads around this question. This means g prime of y equals the antiderivative of f of t, which is capital F of t, evaluated at sine of y, minus the antiderivative of f of t evaluated at 0. And by the way, this is going to be a constant again, because this means you anti-differentiate some function, f of t, and then put 0 in for the variable t, which is going to give you a constant. Now, here is where I really struggled to come up with a reason for why we have to be very careful about the variables. I could, like I did before, I could tell you, well, you know, we could just slap another prime on here, but that's not good enough. And the reason is, and this is crucial, the stuff on the left side is with respect to y, because it's g of y. Y is the independent variable. But this stuff here is all with respect to t, because this is in reference to f of t if we follow that up. So what I'm going to do is rewrite this now. I'm going to take g prime of y, which I reverted back to the prime notation, equals the antiderivative of f of t at sine of y minus the antiderivative of f of t at 0, and I'm going to differentiate both of these sides with respect to y, which is a very odd thing, but it's not f of x, it's g of y, so the independent variable is y. And if I differentiate the left side with respect to y, I have to differentiate the right side with respect to y. If you go back and look at when we had this conversation with the first step, which is the part here that has some work in green, it wasn't a big deal because the variable was y in both sides. Right? The variable, I'll use hot pink here, the variable on the left-hand side was y, the variable on the right-hand side was y. So we could have just slapped those prime symbols on there and nobody would really care because we weren't aware of any differences, because there weren't any differences. Everything was y. But here, there are differences. The stuff in red on the left side has a variable of y, and the stuff in red on the right side has a variable of t. We want g double prime of y, so we have to differentiate with respect to y. This is the meat of the problem here. That since you want g double prime of y, you've got to be differentiating all the time with respect to y. Okay, so now I'm going to, I hope that made sense, but now what I can do is go back to the lazy person's prime notation and say the derivative with respect to y of g prime of y is the derivative with respect to y of the derivative with respect to y, which is the second derivative with respect to y. It's g double prime of y. So now we're going to have the derivative with respect to y of the antiderivative of the function f of t at sine of y, and we're so close to being done here, Brynn, minus the derivative with respect to y of the antiderivative of f of t at 0, and notice I keep saying these are f of t's. This is a capital F of t. This is a capital F of t. The variable there is t. Okay, so how do we find the derivative with respect to x? Sorry, I misspoke. We have g double prime of y. I said x. How do we find the derivative with respect to y of a thing? Well, the derivative, this gets tricky, but the derivative of the antiderivative is simply the thing. So you might say to yourself, since this is an antiderivative and this is the derivative of the antiderivative is going to knock both pieces out and you'll be left with sine of y. But when you differentiate something, you always have to multiply by the derivative with respect to y. So this is, I missed a little thing here that's pretty important. F of sine of y. The derivative of the antiderivative is not just that thing, the derivative of the antiderivative is the function. But when you differentiate something with respect to y, the chain rule says you must now multiply by the derivative with respect to y. So we need to multiply by cosine of y. This is the derivative of t with respect to y. It needs to be added. So I feel as though I kind of screwed up my explanation here with this highlighted part. This highlighted part in yellow is saying the derivative of an antiderivative gives you the original function. The derivative of the antiderivative gives you the original function. They're opposite or inverse operations. And then we have minus, of course, we have this other little piece, which is 0 because the antiderivative of the function at 0 is going to be a constant, and the derivative of that with respect to y is going to be a constant. I see I've got another little mistake here. I don't know why I wrote a y up here. There should not be a y. It should just be d dy. But anyway, the derivative of that constant will be 0. So look at what we have. And that's a powerhouse of a question. We have now a statement that says g double prime of y is equal to f of sine of y multiplied by cosine of y. So now I am going to take a look at what f is, but just a second here. Don't forget, this is where I really had to stop and wrap my head around it. That f here, this f, is f of t. This is a bizarre question. It's f of t, which is the square root of 4 plus t squared. So that f on the right-hand side is represented by this function. So to find f of sine of y, we're going to put sine of y in where there's a t. And I'm going to have the square root of 4 plus sine of y quantity squared. And of course, we know that's sine squared of y. But then I have this, because of the chain rule and how we did this with the fundamental theorem of calculus, we have times cos of y. And now we're almost done, because you want g double prime of y to be evaluated when y is pi over 6. So this will be the square root of 4 plus the sine squared of pi over 6 multiplied by the cosine of pi over 6. So I don't know, if you're a unit circle kind of girl, pi over 6 is here. The coordinates at that point are root 3 over 2, comma 1/2. So the sine is 1/2. We're going to have the square root of 4 plus 1/2 quantity squared multiplied by cosine is root 3 over 2. I mean, you could probably finish on your own, but I'm just going to go to completion here to make sure that I get the same answer that you had. We have g double prime of pi over 6 rather is, boy, talk about being lazy. You're probably so used to not using a calculator, and here I am going to use a calculator to add 4 plus 1/4. It's been a long day. It's 17/4, so we get the square root of 17 over 4. Multiplied by the square root of 3 over 2. So let's see, the square root of 17, the best we can do is write root 17. The square root of 4 is 2, multiplied by the square root of 3 over 2. We multiply across the top, and we multiply across the bottom. And you end up with root 51 over 4, which I believe was the answer. So I hope that helps. I actually enjoyed working this out. And I hope everything's going really well with you, Brynn. Boy, university can be tough, and this is one example of it. I'm just looking to make sure, yeah, that was the answer, root 51 over 4. Brutal question. I don't know. I don't teach university calculus, and I never have, but that's the kind of question where I would say that very few people on an exam would get it right for full marks unless they've done a question just like it. But now that I have done it for you, hopefully it will help. You can always go back and rewatch this video as many times as you like. Have a good rest of the evening, Brynn. Good luck with your exam later in the week, and take care of yourself, okay?